Thank you very much. It's a great pleasure to be here at Philippe's 60th birthday conference. So I do remember when we met, that was in 2004, as Paul Saint-Justin already explained, and also Jean-Bernard. At the time, the Razumov-Stroganov conjecture was the big thing, and Jean-Bernard Subert had certain conjectures on certain components of this vector that was of interest, and together Jean-Bernard, Philippe, Paul, they realized that the 6-vertex model for certain connectivity patterns collapsed to the 5-vertex model that was on Paul's on one of the pages of Paul Saint-Justin's talk. And 5-vertex model, this means rhombus tilings, domino tilings on a hexagonal grid. And so they invited me to come over to Saclay. Then I was much closer, namely in Lyon. And so I gave lectures on plane partitions, rhombus tilings, determinants, non-intersecting lattice paths, or as we have also seen, NILPs for the non-intersecting lattice paths, since apparently physicists can't survive without acronyms. Right, so we don't have a joint paper, but we did at least one thing jointly, namely we organized, entertained, ran an Oberwolfach seminar where we taught enumerative combinatorics and statistical physics to young people. And Oberwolfach always shoots a photo. Unfortunately, the quality is not very good. But as you can see, it must have rained outside, because otherwise we would standing in front of the geometric artwork that they have in front of the building. But the picture of the participants is much better. There are at least 2 other people in the audience that attended the Oberwolfach seminar then. Is there a question already? 2007, sorry, I forgot to say. Right, so here's what I'm going to do. There will be 2 parts. The first part will be on the enumeration of domino tilings of generalized adstacked triangles. And this is joined with Sylvie Courtel and Frédéric Huang, her former student. And the second part will be on determinant evaluations. And this is joint work with Christoph Kutschan and Michael Schlosser. Probably you won't be able to distinguish the parts, because in the first part we also need determinant evaluations, but I hope to point it out. Anyhow, everything starts with Philippe again, namely with this determinant evaluation, this conjectured determinant evaluation. The number this determinant that you see here, that appeared in his work that was mentioned by Emmanuel Guiter on the 20-vertex model. And what he showed is that for certain configurations in the 20-vertex model with certain boundary conditions, their number was given by this determinant. And at the same time, he also constructed a model of domino tilings of certain regions, where these domino tilings were also counted by this determinant, and he observed that this determinant has a very nice evaluation. But he couldn't prove it. All right, and so you see, whenever there is determinant, people who know me know that once I see this, I get hooked, and that was no exception, so I did get hooked. So the first thing is that I like determinants with parameters better, and so I've cleverly left some space to put parameters parameters, one parameter. So I observed if you stick in an x at these places, then you have a very nice evaluation. I have expressed the result in terms of these shifted factorials. Alpha sub m is defined in the usual way, alpha times alpha plus 1 up to alpha plus m minus 1. All right. And I even found a variation of it. So this is a variation. So remember, I go back. So there's a plus 1 at these places. And if you forget the plus 1, then there is again a nice evaluation. But I was not able to prove these evaluations, even with this generalized version. So Christoph Kutscher, he was able to prove the Francesco's conjecture, that is without the x, or x equals 0, by using Zeilberger's holonomic Ansatz. So I will not say much about it, but I should say that this holonomic Ansatz is a very clever way to do determinant evaluations if they work. If they work, then it's algorithmic, so then it's essentially automatic. And in the case of Philippe's original conjecture, that works. However, for the X generalizations, it didn't work, not because of the holonomic ansatz would not work. Probably it does, but the computations become too large, so that today's computer will never finish, but eventually crash.
Can't you do that x determinants with given x, say x equals 5, 6,
Yes,
7?
yes, sure. Yeah, then it would work. Yeah.
And if the answer is an ansatz, from those answers you could get an ansatz.
Sure, you can try, but I think this is rather hopeless.
Okay.
Right. So then, more or less 1 year later, I was in Oberwolfach, and Sylvie Cortel talked to me at some point and said that she wanted to count certain supersymplectic tableaux of rectangular shape, and the computer says that there is a nice product formula for them. And she said a bit more than just that. She was more specific, and so I said, I will have a look. Then the next day, Sylvie reminded me, so what about that? And so I answered, you have to evaluate the determinant. Well, that was not quite new for her. But she also added that the Francesco's conjecture determinant evaluation would be a special case. So I can delete the question mark up there. Oh, now it's wrong, but now it's right. Okay, so let me explain these domino tilings of Aztec triangles. Here's the Aztec square. And here's a domino tiling of the Aztec square. And it is a famous result of Elkis, Kuperberg, Larsen, and Propp, that the number of domino tilings of this Aztec diamond of size n, so essentially the length of staircase on one side is n, is given by this very nice power of 2. Philippe, in his paper, looked at what he called Aztec triangles. It's such a region. I guess it's debatable if this is a triangle or looks like a triangle, but that's okay. So essentially what it is, you have a staircase on upper left, a unit step staircase, and lower right you have a double staircase of the same length. They are of the same length. And here is a domino tiling. And if you now put the Francesco's finding that this is given by the number of tilings is given by this determinant and Christoph Kuchan's computation together, then we get that the number of domino tilings of an Aztec triangle of size n is given by this very nice product formula. Right, and now a generalized Aztec triangle. So now the staircase on up left and the double staircase lower right, they are not of the same length anymore. They depend on two parameters now, n and k, say. Again, so there's a tiling. And there are actually two types. You have to look at the bottom. So I go back to the other. So here's the other. So here you have two little steps, and in the other type you have just one little step here. So there's type 1 and type 2. And they observed that the number of domino tilings of the NK Aztec triangle of type 1 is given by a nice product formula, and same for Aztec triangles of type 2. It's again given by a very nice formula, and if you look a bit closer, then you will observe that it's the same formula, except that we have replaced here n by n plus 1/2. Right, so here is this triangle again. So now I want to explain how you can use non-intersecting lattice paths to count the domino tilings here, or probably here I should better say NILPs. First, we need the checkerboard shading of the ground region. And then on the left, at each black cell, in the middle of each black cell, you start a path. And the rule is that if you have a vertical domino, then you go diagonally across, like here, but it could also be up like here. And if you have a horizontal domino, then you just go right. And what happens now is that you will end up on the right boundary with these paths, and they will end up in white cells along the double staircase, which is bottom right. So let's forget about the region. We get a collection of paths which can have three types of steps, and quite obviously they are non-intersecting in the sense that they don't have any common points. So what I have done here is that I rotate the picture a bit, and then I flip the picture and I embed it into a grid, into a lattice. So here is now this collection of paths. We can forget about these two paths because there's just one way to connect these starting points with these endpoints, and then the starting points are along a diagonal, an anti-diagonal, and the endpoints are horizontally, and the distance of the endpoints to each other is 2. And yeah, right, that's it. And now the theorem of Lindström-Gesell-Viennot tells you that the number, so this is a bijection between this kind of paths and the tilings. We want to count non-intersecting families of non-intersecting paths with these starting and these endpoints, and the theorem of Lindström-Gesell-Viennot tells you that this is given by a determinant. Here it is. It's the determinant of this matrix, and in this matrix the D, M, N are so-called Delanois numbers, these are the number of paths from 0, 0 to mn, which consist of 3 types of steps: horizontal, vertical, and diagonal. Very good. So remember, this is for type 1. For type 2, if you do the same kind of thing, then you get the determinant of this matrix here, where you have the sum of 2 Delaunay numbers. So the task now is to evaluate these 2 determinants. And we have already seen what the conjectured results are. Right. So the Delaunay numbers, they have formulas. You can do coefficient extraction in the generating function, or you have some expressions, but there is no simple formula. It's not a product like the Catalan numbers. This is one of the difficulties that you have to face here. But anyhow, we want to do these determinant evaluations, and I will first concentrate on the first determinant. All right, and I have rewritten the right-hand side now in a very complicated way, you think, but we need this kind of rewriting. So I have done a rewriting where I can see, so to speak, the type of the factors that you can have. Here you have n minus some integer, here you have n minus some half integer, here you have n plus some integer, and here n plus some half integer. And I have done this because my favorite method for proving determinant evaluations is what I call identification of factors, and others call exhaustion of factors. And this method works if there is a free parameter. And there is a free parameter. This is this n. This n does not depend on the size of the matrix. Right, so I will cut this short. This method works in 3 steps. In the first step, you show that each of the claimed factors is indeed a factor of the determinant. In the second step, you compare degrees, and you show that the degree of the conjectured evaluation of the right-hand side is at least as large as the degree of the determinant. And the conclusion of that is that you have shown that the determinant is equal to what you think it is, up to some multiplicative constant. And in the third step, this multiplicative constant is evaluated in some way. Very good. And indeed, most of the steps, they work quite smoothly. The really intricate one is this one. This is the last factor on the huge result. It's this one here. So I will not try to explain anything. I just show you one identity that needs to be proved to verify that this is indeed a factor of the determinant. So it's this very nice sum of 2 double sums, which apparently sums to 0. So I would not I would not know how to prove this by hypergeometric means, say. But so we are living in modern times, and it's a technical area. So there are many computer programs. In particular, there is Christoph Kuchan's holonomic functions package in Mathematica. And the short version is that then it's a routine task. If you look at the paper, then it's still a few pages to argue, but right, so with this package, you can prove this crazy identity. So let's now accept that we did indeed prove these determinant evaluations, and then we see that the domino tilings of the generalized Aztec triangle of type 1 are given by this very nice formula. And since one can prove that there is a relation between the 2 determinants, and in fact the 2 matrices are very simply related by an upper triangular matrix. Therefore, you see here's this shift. You have also proved the second enumeration result. But remember, there was this x determinant. So does it have to do anything with this? So indeed it does. This is something that I observed only later. Namely, so if I now denote by D1 the determinant that you got for the type 1, and if I denote by D3 the determinant with these binomial coefficients, then it turns out that they are very simply related to each other. And I will quickly go over the proof. I sketch how you prove this relation. And again, Philippe is very important in this, in fact. So what Philippe did was that he proved this relation when y is equal to 0. And his idea is that if we want to compute the determinant of a matrix A with entries Aij, then maybe we want to transform the determinant into something else. In fact, this is what we are trying to do. We want to transform this determinant in the other one. And so his idea was that instead of dealing with the determinant, he dealt with the generating function of the coefficients of the matrix. Namely, there are two operations that you can do with the generating function of the coefficients, so that you get new coefficients, but the determinant will not change because the matrices are just related by an upper or lower triangular matrix, multiplication by an upper or lower triangular matrix. So what we can do is that we can multiply the generating function by a power series in U or by a power series in V with coefficient 1. Then you get new coefficients, but the determinant of these new coefficients, it doesn't change. Or you may replace U by a power series in U with 0 constant coefficient and coefficient of U being equal to 1. Both of these operations, when you go to the matrices, corresponds to multiplication by upper or lower triangular matrices, and therefore don't change the determinant. Okay, so here is this recipe again. And so that means what we need to do is to compute the bivariate generating function for the matrix entries of D1, compute the bivariate generating function for the matrix entries of the other matrix, and then do these transformations to transform one generating function into the other. So here is the first determinant and matrix. So it's not very difficult. I give you the result. If you compute the generating function for these matrix entries, then it's this. And here the capital N is the difference of n minus k. So it's not a very simple expression, but still it's an explicit expression. That is good enough. So what about the other one? For the binomial determinant, you compute the generating function of the coefficients and you get this. And I think I did I say it somewhere? So I will say it later. In the end, we will have to specialize x to 2 times capital N. So here are the two generating functions. So now I say it, x will be equal to 2 times capital N, but even if you do this, then these two generating functions don't look the same at all. So this is what you have to do. You take the first generating function, the one on top, you multiply by 1 minus v to the minus n. Then you do this substitution, replace u by this function in u. So you see, both of these operations are operations that are allowed. The first is multiplication by a power series in v, which has constant coefficient 1. The substitution here is a substitution by a power series without constant term and coefficient of u equal to 1. Then you multiply the result by this power series here, and then you check, and you will see that by doing these transformations, the first generating function becomes the second one. You will probably ask, how does one come up with this? You have to ask Philippe. So the only step that I had to add is the first one. This is something that Philippe didn't have to do, because remember, capital N is n minus k, and n equals k is the case that he looked at. So this is just multiplication by 1 in his case. But the other steps, these are the steps that he did, and they work for the more general thing as well. Very good. And so if we accept this, then we have now proven this determinant evaluation. And so for the second determinant, where I skip the plus ones, is quite similar. You can also relate it to the determinant D1 by a similar sequence of operations of generating functions. Right. So now we switch to determinant evaluations. So here's the first one again. Particularly Michael Schlosser started to experiment. So if we have this nice evaluation, maybe there are more of similar kind. So similar kind, what does it mean? So here's a power of 2. Let's look at other powers. So a, say. Then we also allow a shift in the exponent. And then in the binomials, you have everywhere 2j. Replace it by bj. Maybe for other b's, there's also something. Right, and then there's this shift in both. So let's do a shift gamma here. And a shift delta over here, and in the bottom, a shift alpha, shift alpha. Let's try what we get. Are there other instances of nice evaluations when you specify A, B, alpha, beta, gamma, delta? So I start with the same choice that we have taken here for A and B. So the A and B here are 2. And let's call the corresponding determinant with alpha, beta, gamma, delta still not determined. Let's call this D, alpha, beta, gamma, delta of n. All right. Then the first determinant evaluation would concern this determinant, and the second one would concern this determinant. Right, so for alpha, beta, gamma, delta, essentially between -9 and +9, Christoph Kutschan made an automated search, whether there are more nice evaluations, and there are many more nice evaluations. So we found 26. That is, if you go further, probably there are even more. And I show you some of them. So here are the first 3. Here are more, and then so there are certain relations that are very simple to prove, but since they are expressed in terms of the ones that we already know what they are, these are further determinant evaluations. Right, so it's 26 in total. And all these can be proved by means of the holonomic ansatz. Very good. Let's go.
When is small with respect to the total number? Because that was 26 is a tiny fraction of your tries, because that was roughly 10 to the 4 or something.
What was 10 to the 4?
Alpha, beta, gamma, delta were ranging over.
Oh yeah. No, this is expected. If you take an arbitrary choice, then there will be nothing. This is obvious. Yeah?
Yes, but 26 is neither small nor large.
That's the okay. I have nothing to say against it. It's still quite a number. Right. And there were 2 infinite families, as you have seen. Right, so A equals B equals 3. So now there's 3 to the something and 3j everywhere. Again, we looked in some parameter space. And again, we found 26. I think that's a coincidence. So here are the first few, next ones, and then again there is a relation. So it's 26 in total. And again, you can prove all these by means of the holonomic ansatz. The question is, of course, is there an infinite family? And indeed, if you look closer, then there seems to be 3 infinite families, in fact. But these are a bit strange in the following sense. So let's look at this one here. So this depends on x. So the first thing that is strange is that the x here has to be a positive integer. And second, it's bounded above by n, the size of the determinant. So if you go further, then the result is not true anymore. And the dependence on x is just sitting in these 2 funny functions. And then in this product, there is no x. Even if, so they have a similar pattern, and even this somehow points to, maybe you have to do a few manipulations and then it will follow. We were not able to do it. So this remains a conjecture. Now A equals to 4 and B equals to 2, 4 to the something and 2j. Again, we searched in some parameter space. This time we found 16. Here the first, so it's similar to before. And again, all this can be proved by holonomic ansatz. And again, is there an infinite family? So yes, there are 2 infinite families in some sense. So here's the first one. This determinant evaluation, where as in Philippe's original determinant, you have +1, +1. But the difference is this power of 4 instead of 2. So this is not easy to prove. No, it is. So even if there's then x, the holonomic ansatz can prove it. And there's a second one. So this one here, it's a bit different because now the result is not completely factored. There is an irreducible factor of degree 2n minus 2 that remains. Nevertheless, this is a theorem, that is, we can prove that all these linear factors appear, but this is quite lengthy. And now you will probably ask, and what is this polynomial? do we know what the polynomial is? We don't have an explicit formula, but experimentally, we have a recurrence for the polynomials, 3-term, what is it, 4-term recurrence. It's not very complicated. Here are the initial values. We don't have a proof for that. So the last thing, I believe, is A equals 2, B equals 4. Again, we searched in the parameter space and we found several. But now all these are conjectures, because now even that there is no x, the calculations become too big. But there are several nice evaluations, so it's in the range of 10 or so. So we believe that the holonomic ansatz would work, but with today's computers, it doesn't work. Okay, then I believe I'm at the end. I leave you with a rhombus tiling of such a generalized Aztec triangle, and happy birthday. Thank you very much. We have time for a few questions.
Yeah, so I guess a natural question is, do any of the infinite families correspond to a more general domain?
It's a good question, but I have no answer to it. I don't know.
I would add, are these guys integers?
Which ones?
Well, your generalizations.
Which generalizations?
One of 26 times, do they evaluate to integers, these determinants?
Of course, because you start with a determinant of integers.
And alpha, beta, gamma, delta always?
Yeah, of course.
Yeah.
If alpha, beta, gamma, delta are integers, then we will get integers. But
I see negative integers, though, right?
here? Oh, yeah, but
in your gamma functions, I see also.
yeah, that's okay. This is still a binomial coefficient.
Okay.
If you would get a problem if the exponent of the power is something negative, which I think is never the case.
Okay. So in principle, these things could count something.
Yes. But so he asked already the question, I don't know whether they do. So even already, no, yeah, that's right. Yeah.
Even easier case is maybe just to put some weights on the tiles, like horizontal versus vertical, H versus V. Does the product formulation still hold or not?
I doubt, but we didn't try. So again, I doubt, but who knows? So we did try to find some Q analogs of, say so you asked about the combinatorial Qification, if you want. You can also try to put Q binomial coefficients here, and only in one primitive case we were able to find a Q analog, but in most cases we don't know, which doesn't say that there is no Q analog.
So the interpretation would be counting paths with area term, area under the path.
This is unlikely because maybe. I think he was more thinking of that certain directions get a weight. Yeah, I don't know.
And did you, maybe in those many cases, there will be some which share in the result the most of the factors, and they are different only for some smaller factor. In those cases, maybe the relation between the two is expressible through this group of transformation of the bivariate generating function.
I closed over this. So these relations, they are simple to prove, actually.
So they are either so simple.
Most of these relations are simple to prove by usually you just manipulate the first row or the first column. I forget. This is right, but yeah, if you have such a relation and you have not proved the evaluation of neither of the two, then you still don't have proved it. No?
But still, what I had in mind is at a point you had this list of 3 transformation on VU. For example, U going to U over 1 minus U, 1 minus 2U.
Yeah, but this had a different purpose, namely to go from this determinant of Delanois numbers to this determinant of with binomial coefficients. This is a very non-trivial transformation.
I was guessing you put U over 1 minus U, 1 minus 2U, 1 minus 3U, and you get the A equal B equal 3. Too naive.
I think it's too naive. Huh?
I tried that.
If there are no more questions, then let's think.
Naive question, maybe in the identification of factor. So you want to show that the determinant vanishes at some point, or
yes.
How do you handle multiplicities when you have several times the same factor?
You have to find. So let's say. So in other versions of the talk, I have this also on slides. But if you want to prove, say, that x minus alpha to the power e divides the determinant, then what you have to find is e vectors in the kernel of the determinant, or the co-kernel of the transposed kernel of the matrix. So we have to find e linearly independent vectors in the kernel.
So it's a fact of linear algebra.
Yes.
Okay, let's thank Christian again.